Good morning to everybody. It is my pleasure to present a new topic, which is devoted to photophysics of organic molecules. And the main task of this work will be how we can modify photophysical properties and particularly photoluminescence emission of organic molecules using different nanoparticles. So if we tell about nanoparticles, we can use different materials, which consist of different composition, different sizes, different surface modification, and all these nanoparticles can induce different effects when they interact with organic molecules. For example, they can produce synergetic photothermal effects, they can produce sensitization effect, plasmon enhancement effect, up conversion and down conversion of energy, mediation of intermolecular energy transfer, and so on. In this presentation, I will tell about several kinds of nanoparticles which can modify photophysical properties of organic molecules. Namely, I will consider carbon quantum dots, which can influence enhancement of Anti-Kasha emission of organic dyes. Then I will consider plasmonic nanoparticles, both of semiconductor and metallic nature. And I will show you how these nanoparticles can enhance Anti-Stokes emission of organic dyes. And finally, I will tell you about Mathews nanoflakes, which have interesting properties, which can emit, which possess thermal emission, and which can also influence Anti-Stokes emission of specific organic dyes. So first, in order to understand why this topic is important, I would like to tell about light harvesting by photovoltaic cells. As we know, the solar spectrum, which is shown here, it has a maximum in the visible range, in the green part of the spectrum, and most materials which are applied for development of photovoltaic cells just absorb light in this region. But significant part of the solar energy, which belongs to the infrared and ultraviolet region, remain unused. And moreover, when we deal with, for example, absorption of ultraviolet photons by the materials, we can see that because the band gap of the materials usually have smaller value, correspond to the visible range, part of the energy become lost and goes to the thermal energy. And if we consider infrared part of the spectrum, the energy of these photons is not enough to absorb by photovoltaic materials. So we need to to explore a new possibility how we can use this tails of the solar spectrum in order to get more energy from the solar from the sun. One option is so-called up conversion and down conversion of energy. When we absorb infrared photons of low energy, and for example, when we combine two photons of low energy and produce one photon of higher energy, this process is called up conversion of energy, and this allows to convert this low energy to the visible range. The other process, when high energy photon in the ultraviolet range is absorbed. It can be split into two photons of lower energy, and these two photons can be absorbed by photovoltaic cell. And this process is called down conversion of energy. So we can think about how we can use nanoparticles in order to help photovoltaic materials based on organic dyes, for example, to collect energy from the infrared and ultraviolet part of the solar spectrum. Okay, and so and also we need not only to collect energy from the ultraviolet and infrared things of the solar spectrum, but also we should prevent losses of energy, because as I told you, when a material absorbs ultraviolet photon, part of energy goes to the heat. So in order to solve this problem, we can use the phenomena of singlet fission of photons, or we can use Anti-Kasha photoluminescence emission and Anti-Stokes photoluminescence emission, which specific photophysical properties I will tell about and explain you how they look like. So the most simple way of up conversion and down conversion of energy is shown here. For down conversion, we have specific molecules which have triplet energy levels. And when we absorb photon to the singlet level, as a result of interaction of these molecules, this photon can be split into the two photons. And in this way, we can realize the exciton fission or down conversion of energy. The other process is an up conversion. When we have triplet excitons, for example, two molecules with triplet excitons, which transfer energy to the other couple of molecules here, and as a result of interaction of these two molecules, they produce one singlet exciton with energy higher than the energy of triplet excitons. And in this way, we realize the up conversion process of energy. But these processes are rather complex. They require specific conditions and specific materials, and they are not cheap, they are rather expensive. So in this work, I propose more simple ways to use infrared and ultraviolet photons, which concern anti-Kasha and anti-Stokes emission of organic molecules. So what is anti-Kasha emission? Anti-Kasha emission means that when we absorb when we excite electron from the ground state to some higher energy levels, not the lowest energy level, but some higher energy level. And a Kasha rule, in principle, prohibits emission from the higher energy levels, because there is very quick relaxation due to the vibrational relaxation and internal conversion, which are very fast processes. They immediately relax electron to the lowest energy level from which we can absorb Kasha emission. For anti-Kasha emission, when emission comes from the high energy level, we need specific conditions. And I will show you how we can realize this emission using specific nanoparticles. And the other process is anti-Stokes emission, when emission energy is smaller than the excitation energy. So here you can see the absorption to the first excited level, this one, yeah, from some vibrational energy level. and emission from the S1 level to the ground state. The energy of this emission is higher than the absorption energy from the vibrational manifold of the molecule. And I will show you how we can use this phenomenon, how we can enhance this emission, because usually this emission has a very low quantum yield, but using specific nanoparticles, we can enhance the quantum yield of this emission too. Specifically, I will tell about infrared dyes, the structure of which is shown here. And these dyes have a fundamental absorption and emission in the infrared. For example, this dye has emission near 900 nanometers. And we also can observe Anti-Kasha emission of these dyes in the green part of the spectrum. But usually the quantum yield of these processes is very low. Here you can see the quantum yield of Anti-Kasha and Kasha emission, which are less than 1% usually. So the problem is how to enhance the quantum yield of these processes. In order to realize Anti-Kasha emission of organic molecules, as I told, we need specific conditions. Because Kasha rule doesn't allow emit light from the higher energy levels, because the excited electron being on the higher energy level usually immediately relax to the lowest energy level from which the system realizes only Kasha emission. But if we have specific conditions like a big band gap between S1 and S2, for example, we can try to realize the Anti-Kasha emission. Also, we can try to realize Anti-Kasha emission when we suppress the vibronic manifold between this in this band gap, because just vibrational modes are responsible for the fast relaxation of excited electron from the higher energy level to the lowest energy level. So in order to realize, in order to reduce vibrational degrees of freedom, we can design molecules of the rigid structure. For example, we can introduce specific moieties between twisted parts of the molecule, and in this way we can change the radiation lifetime of the molecule significantly. Or, for example, we can realize enhanced emission by so-called aggregation-induced effect, when twisted molecules interact with each other, and in the aggregate, the twisting is suppressed, and emission become more bright in the aggregate. But I will show you the other method how we can enhance the emission by adsorption of molecules on the surface of nanoparticles, the process so-called immobilization-induced emission. So in order we also, when we tell about aggregation of molecules which lead to the higher quantum yield of the emission, we also should take into account that aggregation usually results in quenching of photoluminescence because of excited annihilation of the neighboring molecules. So we need to find a specific balance between aggregation and enhancement of emission. So we can attract nanoparticles, which can help us to enhance photoluminescence. And this enhancement can be realized by different ways. For example, by nanoparticles can provide a template for adsorption and immobilization when vibrational modes become suppressed. Then nanoparticles, if they have electronic free electrons, They can produce platonic effect, which can also enhance photoluminescence by local electric field. Also, nanoparticles can induce conformational change of the molecules. When molecules absorb on the surface of the nanoparticles, they can change conformation, and if this conformation is favorable for the photoluminescence, then we can observe a higher quantum yield of photoluminescence. And also, as a result of absorption, we can also induce improved conjugation of the chromophore. The first kind of nanoparticles which I will talk about is carbon nanodots, which consist of graphitic core, and surface can be enriched with different molecular groups, different atoms like nitrogen, oxygen, sulfur, and so on. And this enriched surface help us to absorb different molecules on the surface of carbon nanodots. Also, carbon nanodots themselves possess photoluminescence. They produce photoluminescence in the blue or green region of the spectrum, and the mechanism of this emission can be different depending on the specific structure of carbon nanodots. So in this work, we used carbon nanodots, commercial carbon nanodots. You can see here the morphology of these nanoparticles and photoluminescence spectrum of these nanoparticles, which have different quantum yield depending on the solvent. And on the other hand, we use this infrared dyes with the different terminal groups in order to interact with carbon nanoparticles. And if we look at the absorption spectrum of these dyes, they have fundamental absorption in the infrared near 900 nanometers, and also they have S2 absorption in the green, in the blue region of the spectrum. And from this data, we can reconstruct the energy levels. So here you can see, and the separation between S1 and S2 energy level is rather large, which is good. That means that we can observe Anti-Kasha emission in these compounds. And indeed, Anti-Kasha emission can be observed, as shown here, by green line. This dyes in solution without any nanoparticles. We can see Kasha emission and Anti-Kasha emission. When we add carbon nanoparticles and realize interaction of this infrared dyes with carbon nanoparticles, we can observe an enhancement of Anti-Kasha emission by about 1 order of magnitude. This is very significant enhancement. So here you can see how the quantum yield of the Kasha and Anti-Kasha emission is changed when we add carbon nanoparticles. For example, for this dye, you can see addition of nanoparticles increases the quantum yield of emission by a factor of 2. For this dye, the quantum yield of emission for Anti-Kasha emission increases by a factor of 4. At the same time, we can see that the Kasha quantum yield for the Kasha emission decreases when molecules interact with carbon nanoparticles. So this is an interesting phenomenon, which mechanism I try to explain the mechanism of this phenomenon, why we see the enhancement of Anti-Kasha emission. First, as I told you, the relaxation from the S2 to S1 energy level of the excited electron is very fast because the processes of internal conversion and vibrational relaxation is of the order of 10 to 11, 10 to 14 reverse seconds. So in order to realize the Anti-Kasha emission, the rate of this transition should be also very high in order to compete with these processes. And indeed, we observed the kinetics of photoluminescence of these dyes. You can see the kinetics change significantly. That means that the rate of relaxation of Anti-Stokes emission increases significantly here. So here you can see the number in terms of the time constant. For example, dye alone has a time constant of emission of the approximately 5 nanoseconds, but in the presence of nanoparticles, this time, 1 nanosecond, but in the presence of nanoparticles, this time decreases by a factor of 4. For the other dye, we observed the similar processes when the relaxation in the presence of carbon nanoparticles decreases very significantly and resulted in the change of the time constant of the emission. The other mechanism which help to realize Anti-Stokes emission is a backbone conformation of the molecule. So depending on the terminal groups which the molecule can possess, this terminal group help the molecule to twist in the solution or on the surface of some surfaces. And here you can see that for Anti-Stokes emission is very high for molecules which have terminal groups consisted of phenol moieties, but Anti-Stokes emission is suppressed when we deal with molecules with sulfonic groups. So sulfonic groups usually facilitate twisting of the molecular backbone. That means that only flat conformation of the molecule help to enhance Anti-Kasha emission. Conclusion concerning the first part of my presentation, I showed you that specific infrared dyes can produce dual Kasha and Anti-Kasha emission. We can enhance Anti-Kasha emission by interaction with carbon nanoparticles by a factor of 2 to 4. And simultaneously, the quantum yield of the Kasha emission decreases by a factor of 2 to 7. And Anti-Kasha emission enhancement is realized due to the enhancement of spontaneous rate of fluorescence by a factor of 3 to 4. And this enhancement is explained by immobilization-induced effect, which leads to freezing the molecule in a specific planar conformation on the nanoparticle surface. So the second part of my presentation is devoted to interaction of organic molecules with plasmonic nanoparticles. And specifically, I will tell about Anti-Kasha emission. So Anti-Kasha emission, as I told, Anti-Stokes emission. Anti-Stokes emission, as I told you, is the process when we have emission energy higher than the absorption energy. So from the first glance, it looks like the break of the energy conservation, but it is not true, because the system uses the energy of vibrational modes in order to realize this process. So here you can see anti-Stokes emission when we have excitation of electron from the ground energy level to some vibrational energy level in the this manifold of vibrational energy levels is called hot band. And from this hot band, we can realize absorption of electron from to the singlet energy level, from which the electron can rise to the ground state with and emit photon with energy higher than the energy of the absorbed photon. In principle, if we look at the emission spectrum of Anti-Kasha emission, it looks similar to the spectrum of the Kasha emission, because the band gap is the same for the materials, but the excitation energies are different. For Anti-Kasha emission, we have a lower excitation energy. For Kasha emission, we have high energy of excitation. But in principle, the spectrum is the same. A specific property of Anti-Kasha emission is that it is dependent on temperature, because higher temperatures improve population of the hot band. That means that the more electrons can fill the hot band, and we can realize anti-Stokes emission with better efficiency. Here you can see the increase of anti-Stokes emission intensity dependent on the temperature. The higher temperature yields higher intensities. And so here you can see the integral emission of integral emission dependent on the temperature, which is a linear function dependent when we increase temperature, and when we decrease temperature, these curves are almost similar. Also, it would tell about hot band absorption. That means that when we excite electron not from the ground state, but from some vibrational energy level, this process is called hot band absorption. This process is also dependent on the temperature. The higher the temperature, the more intensive hot band absorption we can observe. So here you can see, and in principle, this hot band absorption can be absorbed like a small band from the lower energy tail from regarding to the fundamental absorption of the material. So again, the intensity, integral intensity of this absorption increases with temperature and decreases when the temperature is decreased. Quantum yield of anti-Stokes emission is not high. Usually, it is small. So here you can see the numbers for the anti-Stokes emission. And also this anti-Stokes emission is dependent on the excitation energy, because as I showed you, dependent on the excitation energy, we extract electrons from the different depths of the hot band, but population of this hot band is different, dependent on the energy level, which is realized due to the Boltzmann law, Boltzmann population law. So when we use, when we try to enhance anti-Stokes emission, we can apply plasmonic nanoparticles. And These plasmonic nanoparticles can render specific effects on these dyes. For example, when we can increase population of a hot band because plasmonic nanoparticles, when they are excited, they produce not only plasmonic field but also heat. They increase temperature of the environment, which is useful for population of the hot band. And the second process is enhancement of absorption due to the electric field of the plasmonic nanoparticles. So in this work, we used different nanoparticles in order to realize the enhancement of anti-Stokes emission. Particularly, we used the copper sulfide nanoparticles covered with mesoporous silica shell of the different thickness. And also we used gold nanorods, also covered with mesoporous silica. So mesoporous silica is necessary in order to prevent the direct contact of the molecule and the plasmonic nanoparticle, because direct contact results only in the quenching of photoluminescence. We need specific separation between nanoparticle core and the luminescent molecule. And these nanoparticles produce plasmonic effect in the near infrared. For example, these copper sulfide nanoparticles have maximum absorption at approximately 1020 nanometers, and gold nanorods have a maximum absorption at about 1000 nanometers, which is very close to the photoluminescence, to the wavelengths of absorption and photoluminescence of near-infrared dyes, which we used in this work. So the schema of interaction of specific dyes and the surface of nanoparticles is shown here. So because mesoporous silica contain different groups like amino groups, sulfur, nitrogen, and so on, they can interact both by terminal groups and by mesogroups with the surface of these nanoparticles. And so we observed when we realized the interaction of near-infrared dyes with copper sulfide nanoparticles, we indeed observed the enhancement of the hot band absorption, so shown here. So which just prove our concept that interaction with plasmonic nanoparticles can improve population of the hot band and therefore improve the intensity of the hot band absorption. Concerning enhancement of the anti-Stokes emission, the process is more complex, and we use the two dyes in order to study enhancement of anti-Stokes emission. So the structure of these dyes are shown here. They are different by mesogroups only. You can see here the amino group, and here two phenol group linked via nitrogen to the molecular backbone. And we study photoluminescence, anti-Stokes photoluminescence, when we excite with smaller energy than the emission. And we compared the emission of the dyes without plasmonic nanoparticles shown by solid curves and emission of molecules in the presence of the plasmonic nanoparticles shown by dotted curves. So we can see that the difference is very small, at least for this molecule. And if we look at this graph, which describe the dependence of the integral emission on the rover's excitation wavelengths, we see that there is almost no difference between emission of dyes and emission of dyes in the presence of plasmonic nanoparticles. But in this case, for this dye, we observed a small enhancement at specific excitation wavelengths. And so this graph shows more clearly this enhancement. This graph describes the ratio of photoluminescence of dyes in the presence of nanoparticles to the intensity of emission without nanoparticles. So here you can see for two dyes, dye 1 does not show any enhancement, but dye 2 shows enhancement of anti-Stokes emission in the presence of nanoparticles at different excitation wavelengths. For the other nanoparticles, for the copper sulfide nanoparticles, the previous slide was shown for interaction of dyes with gold nanoparticles, and this slide shows the interaction of these dyes with copper sulfide nanoparticles. So again, here we can see, so we used two different kinds of copper sulfide nanoparticles with different shells, and for this dye, we didn't observe any enhancement. So here you can see the ratio of anti-Stokes emission in the presence of nanoparticles to emission without plasmonic nanoparticles is smaller than 1. That means that there is no any enhancement. But for the second dye, we observed enhancement at specific excitation wavelengths. And this enhancement reached 50%, which is very good number. So we used two kinds of nanoparticles, metallic and semiconductor nanoparticles, in order to try to enhance anti-Stokes emission, and we reached enhancement of for this specific dye by 70% when we used gold nanorods, and up to 50% when we used copper sulfide semiconductor plasmonic nanoparticles. Conclusion concerning this second part of my presentation, I showed you that hot band absorption assisted anti-Stokes emission can be used as instrument for energy up conversion with anti-Stokes shift up to 100 nanometers, and in some cases even more. But intensity of anti-Stokes emission is usually weak and is dependent on the excitation wavelengths. And we realized enhancement of anti-Stokes emission by 17% and 15%, dependent on the nature of plasmonic nanoparticles. So finally, in the third part of my presentation, I would like to tell about interaction of vaccines and infrared dyes. Specific of anti-Stokes emission is that in principle it can produce a cooling effect, because absorption we deal with absorption of lower energy photon but emission of high energy photon. That means that part of energy is removed from the system, and the system can be cooled down. And also we can apply specific nanoparticles which produce passive heating or passive cooling effect. And these nanoparticles are MXenes. Particularly, we used titanium and niobium MXenes. They have different thermal emission dependent on the wavelengths shown here. For niobium MXenes, and so titanium MXenes show has very low thermal emission. That means that it can work as passive heating material, because it does not emit heat into the environment, and most heat are kept inside the system. And here you can see an illustration of thermal emission of different MXenes. So the middle part corresponds to the emission of the solvent without any nanoparticles. The left part is solvent with niobium MXenes, and the right part is solvent with titanium MXenes. So we can see that the emission of these two are higher than the emission of the titanium MXene dispersion. So again, we used a set of infrared dyes for interaction with MXenes. And but further, I will show you only the results for this dye, for dye number 3. So here you can see the absorption of this dye, absorption of MXenes, niobium and titanium MXenes, and also Stokes emission when we excite the dye solution and dispersion of dye with MXenes at high energy. So here we can see almost no change for the Stokes emission. But for the anti-Stokes emission, we observed quite significant difference between emission of dyes and emission of dyes in the presence of MXenes. Usually, this emission is suppressed in the presence of MXenes, but this effect is not due to the thermal emissivity, but simply due to the light scattering, because MXenes have a size of the order of lateral size of the order of several tens of nanometers up to microns, and they can scatter light, and therefore the photoluminescence absorbed photoluminescence is suppressed here due to the scattering effect. But in order to clarify the thermal emissivity effect, we studied the dependence of anti-Stokes emission on the temperature. And these studies showed that dependence on the temperature is different for the dyes in the solution without any nanoparticles, dye in the presence of titanium MXenes, and dye in the presence of niobium MXenes. You can see the different enhancement of the anti-Stokes emission for all these cases. And also we can calculate activation energy using this data, using this formula when we have integral emission here and temperature. And we can calculate activation energy, which is shown here, the numbers for activation energy for the different processes. So here I would like to illustrate how the activation energy, what is activation energy means. When we have electron in the hot band, its position can be different depending on the temperature. The higher the temperature, the higher the position of this electron in the hot band, but also it would deal with the passive thermal materials, which improve the which do not allow to dissipate thermal energy outside of our system. Then we can extract electrons which are located deeper in the hot band. And this difference between, this corresponds to the excitation energy. In order to excite the electron, we need the further lift this electron from the hot band from some energy level which is occupied by this electron to this energy level, in order to lift this electron to the singlet energy level. And this gap corresponds to the activation energy. This activation energy is dependent on the temperature and also on the passive heating or passive cooling effect of the system. So for titanium MXenes, we can see that because titanium MXenes provide a thermal heating effect, that means that the system can extract electrons which are located deeper in the hot band. That means that this activation energy is bigger than for the system where we do not have any passive heating material in the solution. So here you can see the activation energy of molecules, 3 different molecules, shown by yellow. Even four molecules, sorry. 4 molecules shown by yellow, and the activation energy of the same molecules in the presence of niobium MXenes shown by green, and in the presence of titanium MXenes shown by light blue. And also when we increase the concentration of MXenes, we can observe further increase of activation energy for titanium MXenes and the decrease of activation energy for niobium MXenes. So here we can see the systematic change of the activation energy using the passive heating material. And this change corresponds to the increase of activation energy of our infrared dyes. So this can be explained by this cartoon when we have MXenes with different thermal emissivity. Titanium MXenes have a lower thermal emissivity, and niobium MXenes have high thermal emissivity, and this results in the different activation energy of our molecule, because the electron can be extracted from the different energy levels in the hot band, and this means that we can change the activation energy of our system using these materials with different thermal emissivity. So, conclusion concerning this last part of my presentation. I showed you that MXene with different thermal emissivity can influence anti-Stokes emission of near-infrared dyes differently. And specifically, titanium MXene, which possess low thermal emissivity, leads to the passive heating effect, and this yields higher activation energy of infrared dyes. On the other hand, niobium MXenes have moderate thermal emissivity, and which results in smaller activation energy of our infrared dyes. And finally, anti-Stokes photoluminescence itself can be used as indicator of thermal emissivity of MXenes, because this process is sensitive to heat change in the system. Finally, let me conclude, make general conclusions of my presentation. I showed you that nanoparticles can be used as effective instruments for enhancement of photoluminescence emission of organic dyes. Particularly, they can help to harness photons from the ultraviolet and infrared tails of the solar spectrum through Anti-Kasha and Anti-Kasha emission. We can realize enhancement of Anti-Kasha emission by nanoparticle-assisted immobilization, leading to stabilization of planar conformation of the dye chromophore. The Anti-Kasha emission can be enhanced by application of nanoparticles that produce plasmonic and passive heating effects. And in addition to nanoparticles, we should also take into account the chemical structure of dye, which which is also play specific role in production of photoluminescence and change of photoluminescence when these dyes interact with specific nanoparticles. I would like to thank different people, different groups and different projects which helped me to make studies in this field and collect results. And thank you for your attention.